Okay, recording should be started, and I think same deal. I'm also trying to make it a little bit of a habit that the moment the recording starts, I also talk at least a little bit because it gives people a chance to adjust their volume, and then they can kind of scoot into the part of the video when things really start if they wanted to. So I will now save my voice, or I'll call it that. I'm going to drink my third cup of coffee, is what I'm going to do. I mean, it's not really my third cup if I keep using the same cup. And if I didn't completely drink it all the way down and just kept anyway, whatever. Hope your day's going all right. We had in La Crosse, we had some rain, some lightning and thunder, even a little earlier. Uh, Seemed to all finish right before my earlier section even started. Um, I am It's a tiring day. I think it just in part due to the weather, but also, I may have mentioned that I'm in a band and we have not met to practice to keep our distance, but it had been several weeks. And so we had, as a band, kept saying, oh, we should like do a Zoom call or whatever. So we did that. And it was last night from 8 to 10 p.m. And like, I mean, it was good to catch up, but yeah. um, all right. So anyway, the coffee is extra. Words. The coffee is extra strong. Cause yeah. Okay. 40 seconds. 40. 6, 5, 4, 3, 2, 1. All right. I gotta move this over to the other screen here so I can keep track of time. Welcome back. Just a round of announcements. Sorry to do this every day, but I think it's extra helpful right now, um, especially as it's an exam week. So we got an exam on Thursday. Complete that pre-exam assignment by Wednesday, by tomorrow. That curve sketching summary handout is in Canvas. Practice exam stuff is available in Canvas alongside a PDF that just kind of tries to break down some of the expectations for exam 3. In fact, that PDF helps try to clarify this idea of like, wait a second, I've got 5 hours inside 48 hours, or how does this work, right? So the exam, if you can start the exam starting from like a minute after midnight on April 9th, but everything has to be turned in by the end of the day on April 10th. This balances a little bit the fact that I need some time to do some grading. That's a 48-hour window of time essentially, but you don't have all 48 hours to do the exam. You've got to pick a 5-hour window of time. So if you wanted to start the exam at like 7 a.m. 7 a.m. on Thursday, April 9th, you're welcome to do that. You just click into Canvas and start quiz. It's called a quiz in Canvas, but it's really an exam. So you would start it at like 7 a.m. on Thursday, the 9th, and then you would have until noon to get everything turned in. Or you could, if you want, instead, you could like say, no, I need to study more, or I've got my work schedule is preventing me from taking the exam at the time I normally would. So you could instead take the exam on Friday the 10th, and you could like start it at 1 p.m. If you wanted to, and then 5 hours later would be 6 p.m. So you'd have to turn in everything by 6 p.m. So this is an attempt to balance a little bit the complexities of turning in things online with also like trying to prevent this collaboration kind of thing. Like, I mean, I have heard. I'll just comment real quick that some stresses from students of if excuse me, if faculty members can't, I've heard situations where there's been a lot of stress of like, this is when you have to turn it in. This is what, like, so I'm trying to open things up, and yet not too far. Like I understand where some of my fellow faculty are coming from on this, and yet I also understand the frustrations that are involved with work schedules are altered. Watching after a younger sibling. I get there's a lot of other pressures, so this is me trying to meet you halfway on some of these things, but I need you to respect the the rules of this process, and if there's some issues with that, then exam 4 will be tighter. So please respect that. Let's see, what other issue have I not covered from the? Oh yeah, the last thing on this list is quiz today. It's a Tuesday, so please complete that online quiz. And in fact, as far as Canvas knows, other than the titles of these things being different, the quiz really is in the same general format as the Thursday exam is. It's just the today's quiz is one question, whereas Thursday's exam is several questions, like multiple questions, right? But like you submit one picture per question, whether that's a picture of you write on paper and then take pictures of your work, or you want to type and then take screenshots. The whole point is the 5 hours. I'm not asking you to take a 5 hour exam. Like it's not meant to take you 5 hours. I'm just trying to provide a long enough time frame where no one runs anywhere close to the issue. Like I don't want anybody stressed out about the online submission process. So take about 55 minutes. If you want to take a little longer, I don't mind. Maybe take an hour and a half. But I'm not designing an exam that's meant to take up a lot of your time. So respect your own time and don't take forever to do it. Once you're complete, just get the pictures organized and uploaded. I want the whole process in the end to not take you more than 2 hours, maybe even not even an hour and a half, if at all possible, from start to finish. That's the idea. That's the intent. Next slide. Just a reminder on office hours. I actually have not had a whole lot of students from 175 show up for office hours. I think since spring break started, I've had a total of 2, maybe 3. I've had one student show up quite a lot. I think for the student who has shown up, office hours have been very helpful. I just a quick demo. I do have like I have a little app here that I can write on screen. So if I, let's say you wanted to bring something, this is sort of like me writing on the whiteboard in my office. So if you had like let f of x equals 6 to the x power, I'm just making up a thing right now, and you needed to talk about the derivative, we can do that like this. You can, so I can write like there. I've had just so if you were a fly on the wall during office hours so far, you would have heard things like, one student who showed up is like, I'm stuck on this question. So like, okay, the student states the question and I write it down on that little whiteboard app. And then I say, okay, well, tell me your steps. And we start writing some of the things. And then sometimes because I'm listening to the student speak about it, I've written something down incorrectly. So I get corrected. I'm like, no, write it down this way. I'm like, oh, okay. And that works. Or you could, if you are connected on a phone or even from a laptop, you could turn on the camera and then point it at a paper copy of your work and I could see it. That's another option. But an email trying to answer math questions just generally doesn't work, because if you were listening in on the processes that happened, like what has generally happened is like one math question, or like one math problem, let's say, turns into like 10, maybe 15 questions back and forth of like, okay, what do you think the next step is? Or here's my hint, you should factor. And then, because that's the story a lot right now, right? A lot of algebra used, a lot of factoring. And then even with a hint, sometimes I'll say, okay, what'd you get? And the student will say, hang on. And I'll work with the students in my other class and then come back. And then there's an error in the factoring. But like these things are hard to point out by email. Like it's hard to get a sense of like, what are you thinking? How are you thinking about this? If if your expectation is like a completely worked out example just by sending an email, it's like that takes a long time. I can't answer those emails. I really can't. And fully worked out examples, that's what we're doing in class. So I recognize that sometimes the questions in web work are a little more challenging, but they need to be. You need to see what getting stuck looks like. I think The process of office hours has had me a little nervous of like, wait, yeah, these are some questions that bring up a lot of challenging algebra, and it's kind of surprising that people aren't showing up. So I just maybe it's people forgot about office hours, but I just want to remind you the times. I just copied them from my syllabus. If during the times of office hours you're having some issue, especially with the audio, call my office phone number. I've got this forwarding, so I can still answer that. And then if the times don't work out in general, send me an email. We'll set up a time to meet. But the email shouldn't be like, here's my math question. It should be, I would like to meet to talk about math. And then we can set up a time to meet. I should just let you know that the committee that I chair on campus is meeting not every other Wednesday anymore, but now every Wednesday. So right after my office hours end on Wednesday, I've got that meeting. So generally speaking, Wednesdays tend to be a very difficult time for me to schedule to meet because I'm basically back to back, 7:45 a.m. to 4:30 p.m. I will try to accommodate requests the best as I can, though. And I should just comment that if you need, um, the Murphy Learning Center tutors are also available using WebEx. That is the system they're using as well. Okay, I think that'll do for announcements today. What I want to do today is comment that yesterday we looked at global maximums. They are also called absolute maximums. In fact, I think the book prefers absolute maximum, so I'll try to stick to that language. That was new. We saw the procedure for global maximums or absolute maximums yesterday. Last week, we saw the procedure for local maximums, which go by the other name of relative maximums. And you may have noticed there's some similarities and some differences. So today, the whole point is to sort these things out, to really clarify, because I think these things can be confusing. Also, if the four places in this paragraph that say maximum, you replace with the word minimum, same story. There's already so much language, right? Local max is the same language as relative max, and global max is the same as absolute max. If you switch these all with mins, same general story. So the goal today is to sort out some of these things. And I got to comment, if you just try to memorize all these procedures like step by step, okay, step one is this, step two this, I think that creates a big headache for you. I should comment and preview and say that next week we, in a sense, learn a new procedure, kind of. And all of these procedures are difficult to memorize each on their own. The important thing to remember is that derivative is slope. I can't stress enough this semester that derivative is slope. It will help sort out what's going on. So what I want to do is sort of visually try to outline the task of getting local maxes and mins and the task of getting absolute maxes and mins. What's similar about these and what's different? So I'm kind of trying to, I don't know if I could properly call what we're going to show a flow chart, but like if we split down the line here, the stuff that's sort of on the left is going to be related to the task of getting local maxes and mins. Over here on the right, we're going to talk some of the steps about getting absolute maxes and mins. And somewhere here in the middle is the stuff that's common to both. So there's some stuff that in yesterday's new procedure, like, wait, that sounds familiar, because there was something familiar. So let me reveal that the common thing, if you're finding local or absolute, you've got to find critical numbers of f. So what's that involve? It's typically take derivative set equal to 0 and then see what x values you get. Now, what you do with those x values is different for local maxes than for global maxes. And same story for mins. Okay, I'll just stop saying mins, just too much. So what do you do with the critical numbers? Well, okay, this arrow is kind of, and this is not a perfect picture, this diagram, but like I'm drawing towards the southwest, right? So the stuff on the left. So what do? At each critical number of f, that's not even a complete sentence. What you do is you either use the first derivative test or you use the second derivative test. Your choice. Okay. By the way, I should say, I mean, I know we're not like physically in the same space right now, but I would still encourage you to take notes. I mean, with my band last night on Zoom, the couple other teachers in the group, and we were commenting how boring it must be on the student side to attend class in this format. I'm sorry about that, but like, I think one of the things you can do to keep things active is take some notes. So I think having this diagram is going to be helpful for you, and it, like, as you write, it gives you a chance to think about these things. Now, to talk more about the absolute mins and maxes side of the story, once you found the critical numbers, again, that's the common step, you need the actual y values. You got to get y values using f, not using f prime. No, we don't need slopes anymore. So at each critical number, plug into f, not into f prime. I wanted to move this box a little further off to the right, excuse me, to clarify that this was about absolute maxes and mins, but I recalled last section why it's not further to the right, because there's another box over here. There's two other y values you need to get. You need when x is a and when x is b, you need y values. So that's why it says here compute f of a and compute f of b. Then what do? You take all of these y values. So these y values, those y values, all of these y values. So these boxes are both pointing into this. You take all these y values and you just report on what's the biggest y value and what's the smallest y value. Okay, so I don't think this picture is perfect in any sense. It may look a little confusing, but I hope it's not overwhelming. I hope you notice, visually, the key thing I hope you're seeing is that you both procedures require the critical numbers of f. What you do with the critical numbers is different. You either take each critical number and apply first or second derivative test, or you take each critical number and you plug into f directly to get y values. Before we get going, I'd like to review the first derivative test, which should be a little more familiar, but just good to review. The second derivative test is probably less familiar. We haven't spent as much time using it, and in part it's because the book introduces it a little later. I think this is maybe even the first section of the book where they actually introduce it. So we'll review these things. Then we're going to do a full-on example problem where we practice this task. We also practice the absolute mins max task. And then we'll look at a second example which reviews different kind of algebra related to logarithms. I think there's some things that people may have forgotten. So there's a lot to even though technically everything we look at this point is a review, there's a lot of decent review and a lot of algebra to look at today. So first, to review the first derivative test and the second derivative test, I did put the word recall here, so if you don't feel like writing this down because you have been taking notes earlier, you probably have this somewhere already. You start with an x value that we're calling here c, which is a critical number of the function f. And then you look to see if f prime changes from a negative to a positive, and if that happens, then f has a local min at c. Now, I don't memorize this text directly. I see f prime negative, f prime positive, and I think, oh, slope negative, then slope positive. Okay, slope negative, then slope positive. So right at the moment you have a critical number, right when the slope is 0, right at the bottom there, that's got to be local min. That's what I remember. It's not worth memorizing the text of this word for word. That's just painful. Same deal, right? The next bullet here says f prime changes from positive to negative. So I'm picturing slope positive, then slope 0, then slope becomes negative. So that's why you have a local max. The final point is if f doesn't change in sign, if f prime doesn't change in sign at c, then f doesn't have a local max or local min there. So what's going on? Like maybe you have f prime as positive, and then f prime is 0. So it's like you're climbing a hill, and there's like a portion of your climbing experience where the ground is completely level, no change in altitude. And then you start climbing a hill again. So then in this flat part where the derivative is 0, slope is 0, those points aren't considered local maxes or mins. It's not a peak or a valley. It's just a resting place. The second derivative test we have not used as much. So I want to comment about it and say same general setup. You've got x value that's a critical number. And then there's this additional thing here about the slope is 0, right? Derivative is 0 or slope is 0. And the key thing is to see here that when the second derivative is positive, then f has a local min at c. And if the second derivative, when you plug in c, when the second derivative is negative, then f has a local max at c. So we've not seen as much of the second derivative test, and I want to remind you of this thing. You're like saying, wait a second, positive? How is a positive making a min? Shouldn't a positive be a max? Shouldn't positive make a max? But the thing to remember is that when you have a positive second derivative, so if f double prime is positive, then f is concave up. So think about the shape of concave up. You have that cup. So if you have a cup like that, concave up, then right at the moment where the derivative is 0, which is right at the bottom here, you have a local minimum, not a local maximum. So it seems a little counterintuitive if you're just trying to correlate a plus with a max, but it's really here a plus for the second derivative is a min for f. Okay. Um, so and then the first derivative test, I know I already said it, but I just want to remind you, it's easiest to recall if you remember that f prime, that the derivative is slope. So these comments down here, this is not some busy language. It's not me trying to be theoretical. It's me trying to say this first derivative test, second derivative, all this text up here, it's hard to just have it all memorized, right? The thing is, it's this is how I recall, right? The second derivative test, it's easiest to recall if you remember f double prime is about concavity of f. And the first derivative test is easiest to recall what's going on if you remember f single prime is about the slope of tangent lines. That's the most convenient way to remember all of this text. I copied the same tests on the next slide, and I want to, before digging into our example, I want to make some comments about how do you know when to use the first derivative test? How do you know when to use the second derivative test? The short answer is you do you, boo. You can use, did I really say that? This is in the recording now. You can use either the first derivative test or the second derivative test in any situation for any problem that I would bring up in class or in quizzes or exams or whatever. So either test is going to work. That said, sometimes one is more convenient than the other. So in short, and we'll come back to this in a little more detail after the first example, if you find that the second derivative is easy to compute, now you can always compute second derivative test. Sorry, you can always compute second derivative because chain rule, product rule. We've got all the tools to find a derivative, but the question is it easy or is it tedious? If you look at f prime and say, oh, I could do another derivative. If it looks easy to get f double prime, then maybe the second derivative test is easier to use. And the reason is because you only need the value of f double prime at that specific x value c. I mean, boom, right at c. The first derivative test, on the other hand, the place where it's a little annoying is you need the sign of f prime both before and after, right? So look at this language. You need, if f prime changes from a negative to a positive at c, meaning you would if c was 10, you need to know f prime of 9 and f prime of 11. It's so you need f prime at two different places, on two sides surrounding that x value. So in some sense, there's a way in which the first derivative test can be more work because you've got to have two values of f prime. The second derivative test only requires one value. It's right at that x value that we're calling c here. But of course, then you have to compute the second derivative. So if you need to compute the second derivative and that looks awful, then maybe use the first derivative test. So there's trade-offs, and we'll see in the example here. So question, f of x equals x cubed plus 3x squared minus 24x minus 31. So I'd like to look at both parts. Part A, find the absolute max and min of f on the interval, closed interval -5 to 6. And part B is find all local maxes and mins of this function f. Give everyone a moment to write if that's what you're doing. Okay, I guess before digging in, the comment to make first is that part A could have been on our another example yesterday when we started absolute max and min on a closed interval. Part B, finding local maxes and mins, this could have been the work we're about to do for part B could have been an example last week. But nevertheless, I wanted to put these all together right here so that we could compare. The whole point is that little flow chart earlier of what's common in the procedures, what's different about the procedures. We're going to see this kind of all at once. That's the purpose of this. This example is nicer, and then the next example has some logarithms. So part A, find absolute max and min. So we're going to need critical numbers of f, and to get critical numbers of f, we need to find f prime and set it equal to 0. So there's f prime, differentiating one term at a time. You can factor out a 3, you'll notice, and then if you do that, you can factor even more. I didn't show all that work, so sorry to skip some of the algebra, but you give that a try. Factor out a 3 first, and then factor what was in parentheses further as an x plus 4 times x minus 2. The comment here being, if you were to set f prime equal to 0, and I'm looking at this boxed version of f prime, if you set that equal to 0, so f prime 0, or just a reminder, friendly reminder, that means slope is 0, then when you solve the equation, setting what's in the box equal to 0, you'll get two values of x. X equals negative 4, x equals positive 2. So those are the only critical numbers of f, because there's no place where f prime is undefined. Yesterday, in our second example, you may recall that we took a critical number and then we just threw it out because it wasn't in the interval we needed. That's not happening here. Both negative 4 and positive 2 are in the interval, negative 5 to 6. So we don't throw out any x values like we did yesterday. And then here's the common confusion, the very often occurring mistake is people will take negative 4 and positive 2 and plug into f prime. There's no need to do that. We know if you plugged in a negative 4 into here, or into this version, I guess, that you're going to get the value of f prime to be 0. We don't need the slope, right? F prime is a slope. We know that the slope is 0. That's because we set f prime equal to 0. We need, for absolute max and min, think about what we're trying to, the goal is to get the tallest point, the highest point in the graph and the lowest point in the graph. So we need actual y values. So what we're going to do right now is compute y values. We need the y values, so we'll plug into f, not into f prime. We're done with f prime. We used f prime just to get these two x values. Now that we have the x value negative 4 and the x value 2, we'll plug those into f. You also notice here we're plugging in these other two x values, negative 5 and positive 6. Those are the endpoints. We plug those into f. So I'll pause for a moment. Not that you need to write down all this algebra work. I just want you to see what was going on. Plugged in negative 4 into f. F is up at the very top. Up here. Plugged in 2 into f. Plugged in negative 5 into f. Plugged in positive 6 into f. So the final two x values of negative 5 and positive 6 we plugged in because these were the endpoints. Remember, for absolute maxes and mins, you have to check the endpoints. I need to make the comment that this question is not super awesome as an exam question. I mean, there are times where a question is better for in class to help demonstrate the concepts. This is better for like reviewing concepts than it is being an exact exam question. It's kind of somehow how things are. Like when a question has not enough moving parts, it's harder to see what's going on. This question actually took me a while to develop, so I know the numbers look strange and there's numbers as big as 149, but it took a long time to make sure that a number that appears as an x value in this question did not also appear as a y value. I think when that happens, it can look a little confusing. And today's goal is to help try to sort out any confusion that might have been introduced from yesterday. So I know the numbers are strange, but this is the best I could come up with to make this all work. We are now so sorry how this is aligned. It's just the minus signs kind of ruin the aligning of the equal signs and so on. But I just circled the 4 y values. And we're supposed to ask ourselves, what's the biggest and the smallest y value? This question is not so bad, right? Like, obviously, the smallest y value circled is the only one that's got a negative sign, right? And then the largest is 149. So this next bullet point is not that you can't see this. Of course, you can look at 4 whole numbers and tell me which is the biggest and the smallest. This is about the language. So f has absolute max of 149 at 6. The smallest y value is negative 59. Yeah, so f has absolute min of negative 59 at 2. What you'll notice here is I left out, I didn't say of y equals negative 59. And then right after the word at, I didn't include x equals. I could have, and yesterday you saw a lot more of that kind of thing. I'm just trying to wean you off of that, just to try to get you to remember that the value would be the y value, and then at is this word that helps indicate we're talking about the x value. So that's the entirety of part A. I will pause, see if we've got any questions from the crowd. Like yesterday, I do want to just take a brief look at the picture. So you could, if you download the slides from Canvas, you can click on the link later, but I already clicked on it and have it open in a window. I just need to move things over. Um, and so the entire function is shown, just like yesterday, the entire function is shown in red, but we were not supposed to look at the whole function. We only were supposed to look for x values between -5 and +6. So I'll hide the graph in red. We're just looking at the portion that's in blue shown here. And you'll notice that um, that biggest y value was 149. In fact, from the slides earlier, we said I actually have it over here. This text, so we said f has an absolute max of 149 at 6. So you see that right there, right? Y value 149, x value 6. That's the tallest, that's the highest point in the blue graph, the blue portion of the red graph. And then the lowest point in this blue graph is down here. And you'll see that that's, so the y value -59, right? So absolute minimum of -59 at the x value 2. So that language is right there. The other thing I wanted to comment on, and I copied this essentially from the slide, just so we could see it all right here without going back and forth between different windows, is we said earlier that the critical numbers of f were -4 and +2. Remember, those critical numbers were found by computing f prime and setting equal to 0. So we should see that in the picture here as well. The critical numbers are the places in our picture where f prime was 0. And remember that f prime is slope. So take a look. Look right there at that peak. That's a place where the tangent line has slope 0, right? Remember, f prime is tangent line slope. So right at -4, right if you were to draw on the tangent line, that ski pole has slope 0. Same deal down here, right? This point down there where x equals 2. Aha, that is the other x value. We computed, we expected, because we solved and got x equals 2 by setting f prime equal to 0. We should see in the picture that's a place where f prime is 0. And yes, in fact, the slope is 0 right there. Yes, I'm using the computer to draw the function, but like it's not surprising that the slope is 0 there. We computed this without having to graph, which is the neat feature of what we did here. Okay, let's move on to part B. Finding local maxes and mins. There is some of the work from part A that we get to copy. So top of the next slide, I have the question printed up there. I have the function up in blue for reference. Here's the stuff that we don't need to repeat the work on. Like I'm not going to go through the steps again, but we computed f prime. We factored. Right here, we got these two x values, -4 and +2. That's when f prime equals 0. Now, let's talk about what's different from the process of finding absolute max and min. What's different is now to find local maxes and mins, you have a choice, recall, at each of the critical numbers. So at the critical number of -4 and the critical number of 2, you have your choice of using the first derivative test or the second derivative test. Either way works. I'm going to show you both options. So if you use the first derivative test, first, where's f prime undefined? Well, that doesn't happen. So only if we're building a complete sign chart for f prime, the only x values to show on the f prime sign chart are -4 and +2. So I didn't show you all the stuff. You know, the plus minus plus, like I had to pick some x values. You know, these are the only two vertical tick marks. So don't just because you picked x is 3, which is probably what you did, that you don't want to include this because that looks confusing later. You might start picking even more x values. But so this is what the completed sign chart looks like. So I probably picked x is -5, and then probably picked I don't know, x is 1 for the part in here, and then I probably picked x is 3, and I plugged those into f prime now because we're building an f prime sign chart. Right? That's already different from part A where you had to plug into f to get the actual y values. You got to keep track of what the heck you're actually doing to do this. So the reason we have this f prime sign chart is because the first derivative test says things like if f prime changes from positive to minus. And so the sign chart helps us see this rather quickly. So take a look. F prime goes from a positive to a negative at this x value -4. Right? Before you have a positive f prime, and then right after you have a negative f prime. So think about what that's creating. Positive slopes and then negative slopes. That's creating a local max. So there's f has a local max at that x value of -4. Then at the next critical number of 2, f prime goes from a negative to a positive. So negative slopes followed by positive slopes. So that's why you have a local minimum. Create that shape of a valley. Local minimum at 2. That's using the first derivative test. I think that sounds a little more familiar. It's the one we've used more often. But I want to show you that you can get the same final answer using the second derivative test. So for the second derivative test, we need a second derivative. Take a look. F prime is up here. You could use the factor version, but I'd rather not because you'd have to use the product rule. So it's actually more convenient to use this version, the unfactored version of f prime. When you take another derivative, so f prime prime is equal to 6x plus 6. Differentiating 3x squared plus 6x minus 24. The 24 is a constant and differentiates to 0, right? Okay, the neat thing about the second derivative test, so in this example, I'd say the second derivative was not so bad to compute. Now, instead of like looking before and after, which that's why we drew out an entire sign chart, now we just need to plug in these two specific x values of -4 and +2 just directly. Like, boom, that exact value of x. So I plugged in -4 first into f double prime. So plug in f double prime -4 equals plug in for the x. Okay, so 6 times -4 plus 6. Now, I don't even really bother computing the number completely. I could have done that. The only thing is we just need to know, is this number negative or positive? And there's enough written here to see that the number should be negative. And so if f double prime is negative, then if you were to picture f originally, then f would be concave down. And so that concave down shape would create a local maximum, right? Yeah. So that's why it's written here. I didn't even look at my slide. I was just trying to reason my way through because I don't have the second derivative test memorized word for word. I try to just reason through it each time. The other special x value here was x equals 2. So you plug in 2 into f double prime into 6x plus 6. And look, there's no minus signs anywhere. 6 times 2 plus 6, you could compute the number directly if you want, but there's no minus sign, so that number's positive. In other words, second derivative positive, so the original f is concave up. And if you have concave up, that means you've got to have a local min right at the bottom, right where the slope is 0. So that local min, we're reporting right there by saying local min at 2. So, yeah, we're done. I guess I'll just comment that you get the same final conclusion of local max at -4, whether you use the first derivative test or second derivative test. You get the same conclusion about a local min at 2, whether you use the first derivative test or the second derivative test. So these are both options, and I just wanted you to see both options. I should also comment that I know we just looked at a picture at the end of part A, but all this part B work, we can do this without looking at the graph. So I'll pause, see if we have questions. Okay, question came up. It just disappeared on that screen. I'm gonna look over here. Can an x value be a local min and an absolute min? Yes. That's a good question. That's a fantastic question. So let me I'm gonna make up an example right on the spot, if that's cool. So let me just give myself a little space here. Okay, so not related to this. Oh, you know what? I forgot. I've got this little whiteboard. So this is me pulling up we're in Centennial. That screen is moving up slowly. And now here, I'm gonna introduce a function, not by formula, not like writing an x, because right at the top of my head, it's just not gonna happen. I mean, give me some time if you really want it. I mean, there is some old example that you could look at in notes, but I'm just gonna draw a picture. Right? So let's see. I gotta read the question. Can an x value be a local min and an absolute min? So how about I'm going to try to create a lot of neat features in this. So how about like, let's say that's the relevant portion of the graph. So let's say you have to look from like x is 2 to, let's just call this 10, right? So you're looking from 2 to 10, and maybe this graph like continues on. So I'll just draw this in like in red. Like maybe the graph continues, but we're not supposed to look at the other part of the graph or something like that. So you'll notice just looking at the portion of the graph drawn in black, it looks like this is the tallest point. So that's the, I know this is not answering the question directly, Allison, but like this point here shows you the absolute max, right? So amongst all the points drawn in black in the graph, that has the biggest y value. It's the highest up point. And you'll notice that this is not a local max, right? A local max would be like, look at the red part as well. And do you have a peak? No, you don't. It's just this point happens to be the highest point only because we artificially cut off the graph because like the word problem that we look at next week says, oh, x has to be 2 or bigger, that kind of thing. So not a local max, but it is the absolute max. I'll point out that the local maxes are these peaks there. I think, sorry if my drawing's a little unsure here, but I'll say that that's just level and not a local max. But these are local maxes over here. There are 2 local maxes. And then for local mins, where are the valleys? There's one, there's a valley right there, and there's a valley right there. So I'll call those 3. I meant this to be level. So sorry. I mean, just trying to draw. There's these 3 local mins. And now let's take a look. Let's see if everybody spots the global min or the absolute min. It's the point with the smallest y value. The lowest point in black is this point right there, right? So this is an absolute min. Now, so right off the top of my head, I can't just come up with the formula, f of x equals and some, x to the 4th minus whatever that produces this picture that you see in red and black. But it's out there somewhere. I mean, if you just made me work on it for an hour or something, I'd come up with it. But here's the picture version that shows this, I hope. So I tried to answer the question, can an x value be local min and an absolute min? Let's say right here in green, you're seeing that. I hope, right? Does that work to answer? I'll pause and see if I get that point is local min and absolute min. Yeah, okay, cool, got it. And then just because why not? Just to show that something more complex can happen, just in the picture, I thought, how about an absolute max that's not a, absolute max that's not a local max. And so you're seeing that too. So I'm trying to show you kind of both things all at once. I not only answered your question, but hopefully even like this additional question that you might have had in mind. Cool. All right. So cool. Creative use of the whiteboard in the middle of. All right. Cool. I'm learning things. Okay. Before we move on, I'll just comment in our last question, having used the first derivative test and the second derivative test, now I can go back and I think it's a little easier to clarify when you might use which one, right? So now that you've experienced both of them side by side, in some sense, the first derivative test is slower because you need to compute f prime on both sides of that x value. You need a little before, like was our plus sign, and a little after is our minus sign. And in some sense, the second derivative test is slower because you got to compute not just f prime, but you need f double prime. So there's extra work for using the first derivative test or for using the second derivative test. But if each is slower than the other, then each is also faster than the other, right? So in some sense, the first derivative test is faster because you don't need to compute f double prime. And in some sense, the second derivative test is faster because you don't have this annoyance that the first derivative test has, where you need the value both to the left and to the right of that x value. You just need the value of f double prime right at that x value, right? Not before and after. So these are all trade-offs. It's like one isn't always faster than the other. I guess that's my point. There's like you've got to just try them both out. I would suggest that you don't. I think sometimes people get in the habit of, oh, I'm just going to always use the second derivative test and never use the first derivative test. I wouldn't do that. I would say I encourage you to learn how both of them work and try them out and see, oh yeah, this one seems better. Like sometimes one takes way more time than the other. So it's good to just try them both out for a little while so that you can start to develop more intuition for like which one to use in which situation. The next question, before we dig into it, there's a lot of algebra review, and I can't cover it all, but I want to review something from week 1. And I want to say, when you see here this log base b of c, this is this is called, by the way, log base b of c. Don't say log b c, don't say log of b, it's log base b of c. That's important. And also, definitely don't say log times c. That I've seen all kinds of people like I've seen in the past people turn that into like a reason to do the product rule when you're doing a derivative. And there's no product going on at all. There's no multiplication. When you see log base b of c, this is asking b to the what power equals c. So we'll look at a brief example because this example shows up in the example we're going to look at. Ln of e squared. First of all, ln is just shorthand notation to mean log base e. Okay. So you can rewrite the ln part as a log base e, and then after saying of this e squared I just copied. Now look at how this fits the format of what's up here. For the b, we've got to plug in e, and for the c, oh my goodness, my foot fell asleep. I know I shouldn't have sat like that. Hang on. Okay. For the c, plug in e squared. So then this question is asking here. Oh jeez, the question is asking here. So e to the what is equal to e to the 2. Right? E to the what equals e to the 2. Now listen to that again. E to the what equals e to the 2. It sounds so silly. You got to just replace the what with a 2. Right? If you in e to the what equals e to the 2, you replace and you'll hear e to the 2 equals e to the 2. So if the replacement in the blank was a 2, this thing simplifies to a 2. This was a brief overview. There's a lot more thorough logs, overview, review from the slides if you look at week 1. And you're going to, if that's rusty, like a lot of algebra is coming up, a lot of factoring, in what we're doing. Like there's a lot of algebra to review. So please look, drop by office hours, ask. There's even some more log stuff coming up inside this question. So I'm going to try to review everything that I can. So the question type, parts A and B, are like before. So the function is f of x equals x over e minus ln of x. Find absolute max and min of f on the interval 1 e squared. Then part B is find local maxes and mins. Both parts can be done without a calculator, I promise. You'll see this here. You just need to keep in mind that e is about 2.7 or maybe even just 2.5. That's all you got to keep in mind. So in terms of process, overall, it's like the previous question, but the logs and the e bring up a chance to review some of the algebra that's going on. First, either of the two parts requires f prime, but you'll notice I didn't write f prime. This is just f. So I didn't want to differentiate x over e directly because that looks like it needs the quotient rule. Keep in mind that e is a number, right? E is approximately 2.7. So I asked myself if I needed to, so 2.7 is close to 3. How would I have differentiated x over 3? I would not have applied the quotient rule. I mean, you would be allowed to, but why? I would just, instead of rethink this as 1/3 x. So same deal. X over e, I'd just like to think of it as 1 over e times x. This is going to make differentiating much nicer. So there's no differentiating yet. We just did a little algebra to rewrite the function. And now to take the derivative, take a look. The derivative of 1 over e times x is 1 over e. The reason is when you have a plain number multiplied by x, the derivative is just that number that's in front of x. Just like think of the derivative of 7x. It's 7, right? So 1 over e is just a number. If e is just a number, there's no x in the numerator. 1 over e is a number, so the derivative of number times x is just a number. And that's what happened here for the first term. And then the derivative of ln of x, just old derivative rules, helping you remind, is 1 over x. We need to ask the usual questions like where is f prime undefined, and then where's f prime equal to 0. So where's f prime undefined? The only danger is when you want to plug in x as 0, because that'll cause you to accidentally divide by 0 here. So f prime is undefined at 0, but for part A anyway, 0 is not in the interval. So we can chuck it out, right? So we found this f prime is undefined at 0, but it's not in the interval, so we ignore it. Now we need to know when is f prime equal to 0. So let's set f prime equal to 0. This is an equation. Equations have equal signs. An equation with fractions. You've heard me say all this week and last week, if you have an equation with fractions, good to multiply by a denominator on both sides. Now, if you multiply just by e on both sides or just by x on both sides, you'll still have fractions. So why not multiply by both? So you see I'm going to multiply by EX on both sides. So here's what I did. I just wrapped each side in parentheses and stuck an EX outside the parentheses. This is multiplying by EX on both sides. On the left side, you can distribute the EX. And there'll be some awesome cancellations from that. So you have X minus E is equal to 0. You can add E to both sides. So the only critical number in the interval, anyway, because we removed the 0. We moved the 0 because it wasn't in the interval, is E. So now for the absolute max mins, it's common as a mistake to try to plug into f prime. And the reason people want to do that, I think, is because it's the most recent function we looked at. But we need actual y values. So you got to go back and now plug in e and plug in 1 and plug in e squared, all three of those x values back into this original f up here. So we need to talk through this because this is where there's a bit of algebra review that comes up. So first, when you plug in 1 in up there at the top, so 1 over e minus ln of 1. Every x up here has been replaced with a 1. We should talk about this. First of all, with the 1 over e stays, but ln of 1, so after the minus sign was an ln of 1, you'll notice that that's a 0, because that's e to the what is equal to 1, and the answer to that is a 0. Again, it's this algebra review of logs is brief. If you need to, office hours, or look at the early, like the third day of class slides. There's a lot of log review there. So I left off the minus 0, and I'll just comment that 1 over e is less than 1 over 2. This is because, think about, the thing is, 1 over 2, e is bigger, right? E is 2.7. So e is bigger than 2. So when you do 1 over a bigger number, so when you divide by a bigger number, like e is bigger than 2, then the result of the fraction is a smaller value. Think about it like 1 over 2 versus 1 over 100. Right? So yeah, okay. And then to plug in the next x value, e, up here, so e over e minus ln of e. Well, e over e divided by e simplifies to 1. Ln of e is 1, because this is e to the what power equals e. So 1 minus 1 simplifies to 0. The last x value to plug in is e squared. So go up here, plug in into the original function, plug in an e squared for every x. So you have e squared over e minus ln of e squared. So the thingy before the minus sign, that e squared, you could of course think of it as e times e. And there's an e in the denominator, so you can cancel an e on top and bottom. So you have an e before the minus sign. And then after the minus sign, ln of e squared, that's what we did as the mini algebra review on the previous slide. So ln of e squared, we said it was a 2. Now, keeping in mind that e is about 2.7, then e minus 2 is about 0.7. And now take a look. We can actually, based on this, see this 1 over e is smaller than 0.5. And then we got 0, and then we have this e minus 2 is about 0.7. We can actually stare at this information to see what's the biggest and smallest y value. So the biggest of these is the one that's approximately 0.7, right? That's bigger than the number that's smaller than 0.5. So, but you'll see I'm not reporting the 0.7 here. I'm actually using the exact value. So this is where if all you do is try to plug into a calculator, you're going to get yourself in trouble. Here, the approximate helps us see what's happening, but we should report when we need the absolute maximum. It is this y value of e minus 2, and that happens at this x value of e squared. Finally, which is the smallest of these circled exact y values? It's 0, right? Because you have a number that's a positive number that's a little smaller than 0.5, or you have 0, or you have approximately 0.7. So the absolute minimum is 0, and it happens at x equals e. Whew. Okay, so now let's take those let's take a look at local mins and maxes. There's a part that we keep the same as before. So the derivative was computed earlier. I'm just copying that from earlier. We found out when you plug in x equals e, that's what makes f prime equal to 0. We also noted earlier that f prime does not exist when you plug in x is equal to 0. All this stuff is useful on the sign chart. And even here, because I want to review the algebra, I did not already put in the pluses and minus signs in these spots. Like it's good right now to review even more algebra. So you need to pick an x value that's to the left of 0. You need an x value between 0 and 2.7 ish, and then an x value that's bigger than around 2.7. So I plugged in, as you might naturally as well, -1. Now here's the funny thing: we're plugging into f prime. Remember earlier for absolute maxes and mins, we needed actual y values, and we plugged into f. You got to always keep all these things in mind. We're plugging into f prime because we're building an f prime sign chart because we're trying to use the first derivative test. Here we need slopes. So you plug into f prime, which is up here. The negative cancel out. So you have 1 over e plus 1 over 1. I don't see any minus signs anywhere, so that number, I don't care what the number is. I just see that the number is positive. There's a plus sign there. Now we need a number between 0 and e. Well, if e is 2.7, you could pick your x value to be 2 or maybe 1. I just picked 2. So you have 1 over e minus 1 over 2. We actually already argued why this should be negative in a sense, because if e is bigger than 2, when you reciprocal both sides, you have 1 over e is less than 1 over 2, right? So we already talked about how when you divide by a bigger number, like e, than when you divide by 2, the overall value of the fraction is smaller. Said differently, think about it this way. We'd all agree that 3 is bigger than 2, and when you reciprocal both sides of this inequality, sometimes people make the error of keeping the inequality symbol in the same direction. This is actually an error. You're like, really? Think about it. The inequality symbol needs to swap, because is 1/3 bigger than 1/2? I don't know about you, but I would rather eat half of a pie than 1/3 of a pie. So if we follow then and agree that the symbol should switch, so it should be 1/3 is less than 1/2, same deal, then 1 over e should be less than 1 over 2. And so if you have a smaller number subtract a bigger number, then the overall result should be negative, should be less than 0. And finally, we just need a number bigger than 2.7-ish. So I just picked 100. Why not? And same general deal is like 1 over 100. That's tiny because we divide by a huge number. And 1 over e is bigger. So bigger minus smaller is going to be a positive. So now having completed the sign chart with the plus minus plus, right over here where there's a d and e for f prime, there's actually the same d and e problem in f due to the logarithm. So the place we need to look is right here at this critical number e. Look what happens. F prime is negative, then F prime is positive. So negative slopes followed by positive slopes, right? So right at the moment when the slope is 0, there's got to be a local minimum right here, right there when x is equal to e. Okay, that's a lot. Just reminder of the announcements. I won't repeat them all right now. I'll just say, just for the benefit of those who may have joined a little late, today the key thing is there's a quiz, online quiz today. Turn in a picture, whether that's a picture from a phone or you can type on a computer screen and take a snapshot of that screenshot. And just reminder, please make it to office hours if you can. I know there's questions out there. I know, just based on even having 1 or 2 people ask. And then finally, tomorrow's stuff does not look at all like what we've done so far this week. Of course, tomorrow's stuff is not on the exam, but I would still join because tomorrow we are previewing one of the key things by looking at some formulas related to area and volume and so on. All right. See you tomorrow or in office hours.